तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome. In the previous session we have been talking about recovery techniques in database management systems. How do we recover a database especially when the database was running and the system was subjected to some kind of a failure, and we saw that there are different varieties of recovery techniques, each having their own advantages and disadvantages. Let us continue with this topic further today and bring it to a logical conclusion by looking at all the other issues that entails database recovery. Let us briefly summarize what we have studied until now. Whenever you are thinking given computer system, whether it is databases or otherwise, is subjected to frequent or non-frequent kind of failures, different kinds of failures, and we could classify failures into different types, like say system failures or media crashes or communication failures or transaction failures. System failures and transaction failures are by far the most frequent or the most common kinds of failures. What is a system failure? System failure is something like suppose you are running your DBMS on a machine and let us say the power goes off and your machine crashes. The characteristic of such a system failure is that all data that are there in the volatile memory like RAM are lost. However, data that are present on persistent storage like disk are still retained. So whatever has made it to the disk can still be retained, however whatever has was still in the RAM is lost. Similarly, there are failures like transaction failures, which are again quite common. Transaction failures entail failures where for a variety of reasons a given transaction cannot is not able to complete its operation. These reasons could be something like too many processes running in the system, or not enough privileges for running this transaction, or the transaction trying to do some illegal operation transaction, and so on and so forth. Okay, and these are again quite frequent kind of failures, and here again the characteristic is that whatever the transaction was doing and whatever data that the transaction had in the main memory is lost. However, the data that are present on persistent storage like disks are still retained. Then there are communication failures where especially if your database is distributed and you have to communicate between two or more different geographically distributed databases, then you might encounter communication failures which need to abort a transaction or leave a transaction midway, and there are somewhat infrequent failures called media crashes, like a disk crash, like a disk developing bad sectors or some kind of damage, physical damage to the disk, where not only data that are there in the physical memories in the primary memory is lost, but the data that are present on the disk are also lost. That is you as well. Now, what is the main property that we have to consider or that we have to maintain when we are talking about recovery techniques? As we all know, transactions in databases follow this well known property of acid, which stands for atomicity, consistency, isolation and durability, right. So atomicity essentially says that either all updates that are to be performed by a transaction are performed or none of them are performed. This is obvious because suppose you are transferring money between two accounts, let us say you have a debit in one account and a credit in another account, either both of them have to be performed or none of them have to be performed. So either the transaction should run fully or it should not run at all and so on. It is not sufficient if money is debited but not credited or vice versa. Similarly, consistency, a transaction when it completes cannot leave the database in an inconsistent state. We have seen some integrity constraints and notions of triggers where suppose database consistency is violated, automatically triggers are enforced which will cause the transactions to roll back in many commercial databases. So if the database starts from a consistent state, at the end of a transaction it should remain in a consistent state. And of course the third property is of isolation, where when multiple transactions are executed simultaneously, for efficiency reasons they are executed in a concurrent fashion, that is the updates made by each of the transactions are performed concurrently. However, the net effect, that is not all possible concurrencies is okay. Essentially the kind of concurrency that is permitted is that the net effect of these multiple transactions should be such that it should be as though the transactions have been executed in some kind of serial fashion. Okay. And the last property is about durability, where once a transaction commits, once a transaction says that I have committed, then whatever changes that it has made is persistent. After commit, it should never be the case that let us say a system crashes after a transaction is committed. It should never be the case that the transaction is now aborted or rolled back. Once the transaction is committed, it means that it has performed some kind of a physical operation, that is it has performed some kind of a operation that is beyond the purview of the database itself. For example, when in an ATM transaction, let us say an automatic teller machine transaction, once a transaction commits, it means that it is safe for the ATM to dispense money. After the ATM has dispensed money, we decide to actually abort the transaction and then say okay, it has not been committed and so on. So once changes that are made by transactions are committed, they have to be durable, that is it has to be persistent. And we also saw that transactions can be in different states, like active or partially committed or failed, aborted, committed or terminated, right. So an active state is the initial state when the transaction is executing, it's performing some operations, it has fetched some data elements and made some changes and so on. And partially completed is a state when it has performed all its operations and it is ready to commit, it's not yet committed. And once it discovers that it is not able to proceed further, whether it is not able to commit or whether it is not able to calculate or perform its computations further, we say that the transaction has failed. Once a transaction has failed, it has to roll back. Any changes that it has made to the database has to be reverted, has to be undone, and once the rollback is complete, we say that the transaction has aborted. And if on the other hand, if the transaction successfully commits, it is a committed transaction, and a terminated transaction is something which has either aborted or committed. So this slide, which is now familiar, shows the different states of a transaction in a schematic fashion. That is, an active transaction can become either partially committed or failed transaction, depending on what it has, whether it has been able to perform all its operations or it is not able to perform all its operations. And from a partially committed transaction, you can still go to a failed state when you see that it is not possible to commit the transaction. But once you see that it is possible to commit the transaction, then you go into a committed state, and once you come to a failed state, you perform a rollback operation where you go to the aborted state in the transaction. What is meant by transaction recovery? Once again, A transaction recovery is the process by which we recover the database system which is performing several different transactions into the most recent consistent state, right. That is at any given point in time any several transactions simultaneously. Now during such a time when there are some kinds of system crashes, let us say some kind of failures like say system crashes or transaction failures or media crashes or whatever, it basically leaves the system in an inconsistent state. Half of some transactions have been performed, some of them have been committed, some of them have just started, and some of them were shown to be committed but may not have been committed, and so on and so forth. Okay. So it is essential that when we recover from this system crash, we should recover to a state that is obviously consistent, and it has to be not just any consistent state, it has to be the most recent consistent state that was there before the crash. And all active transactions around the time of the crash, that is when the crash happened, there were, let us say 10 different active transactions that were running. Once we recover from the crash, of all these active transactions, they should be either in a committed state or a aborted state after recovery. That is either all the operations that are performed by the transactions are persistently stored in the database, or they are rolled back so that they can be invoked once again by the DBMS system. We also saw that there are certain prerequisites for recovery to happen. That is, there are certain kinds of schedules by which transaction activities are performed which are not recoverable at all. For example, this slide shows two different transactions, T8 and following operations. T8 performs a write operation on an element called A. Okay. So it reads an element A and makes some changes and writes it back to the element A. Now let us say T9 reads the new element of A which has been written back by TA and commits, that means let us say it displays. Okay. So let us say it is something like you have just updated the bank account in your bank, or updated your stock price or something like that, and there is another transaction which has read the new stock price or the new balance account and displayed it, or printed a statement. Let us say commit is some kind of a physical operation. So let us say it printed a statement. However, the transaction T8 has not yet completed here, and while it is still going on, it encounters a system crash. And once we recover, we say that T8 has to be rolled back or has to be aborted and restarted again. Now, what has happened here is that this transaction T9 has already said that the new value of A is so and so, and it has already printed the statement or displayed it or done something of that sort. So such a kind of schedule is not a recoverable schedule, that is we will not be able to recover from such a schedule. There is also another kind of problem with recovery, namely that of cascading rollbacks. This slide shows such a example here, that is, even when a schedule is recoverable, sometimes whenever we roll back a transaction, there might be several other transactions that are waiting on it that have to be rolled back, and all of them have to roll back one after the other, which causes a cascade of different rollbacks. So here there are three different such transactions, T, T1 and T2, where T has read the element A and written something back to it here. Now whatever has been written back by TA or by T is now read by T1 and it is written back, and whatever has been written back by T1 is now read by T2. Now but transaction T has not yet committed here, and it is still going on, and then it crashes. Okay. Now after we recover from the crash, suppose we decide that transaction T has to be aborted, it means that transaction T1 as well as transaction T2 has to be aborted, because they have read some changes or they are basically depending upon the changes that are made by T itself. So this causes the problem of cascading rollbacks. So we saw how to prevent cascading rollbacks and non-recoverable schedules in the previous session, which I will not go into more detail here. Essentially, in order to prevent non-recoverable schedules, you need to ensure that no transaction reads a data element that is written by another transaction unless it has committed. Unless there is only after committing a particular operation can another transaction read this transaction. So, okay. We also saw two kinds of log based recovery. What is a log based recovery? Log based recovery uses what are called as write ahead logging, or what are also abbreviated as WLA, write ahead logging addresses, WAL rather, write ahead logging. Okay. Now, what is a write ahead logging? Write ahead logging essentially means that before performing any operation on the database, you perform a corresponding operation onto a log file, and then perform the operation onto the database. Now, whenever the database crashes, you have to use your log file in order to be able to recover from your system failures. We saw essentially two kinds of techniques based on write ahead logging. What are called as in deferred update techniques, the database is not modified until after the transaction reaches its commit point. That is, whatever changes that a transaction makes to the database is first just written to the log, and only when the transaction is ready to commit will the log be written onto the or the changes be written onto the database itself. So, until after the commit point, the transaction or the database is not modified, and once the commit succeeds, you also enter a commit or committed entry into the log. So, essentially whenever there is a system crash, you just need to redo your transaction so that it reaches the point where it has been in. And there are other kinds of techniques called immediate update techniques, where database is updated as and when the transaction progresses. However, as the name write ahead logging suggests, that the updates are first written onto the log before they are written onto the database. And immediate update techniques requires both undo and redo operations. That is, you need to undo all active transactions which have not committed, and you have to redo all transactions which have committed actually. The general idea behind recovery using deferred updates is shown in this slide, and such kinds of that is, there is no undo operation as part of this database as part of this recovery technique. However, there is a redo operations. Okay. Because why is there no undo operations? Because the database is not touched at all, that is the database is not modified at all until the transaction is ready to. A multi-user system, in a multi-user database system, you have to perform let us say some kind of two-phase locking in order to prevent in order to enforce isolation constraint, and all locks, that is whenever you are holding such a lock on a database item, all such locks are released only after the commit. Therefore, no transaction can read any other can read the values written by any other transaction before it has committed. Therefore, there is no possibility of cascading rollbacks, and also there is no possibility of a non-recoverable schedule occurring as part of this recovery mechanism. However, the problem with deferred update techniques is that suppose a transaction performs, let us say some 500 different operations. Now, none of these 500 operations are written onto the database until after the transaction is ready to commit. Therefore, once the transaction is ready to commit, suddenly there is a huge spurt of activity. Suddenly there is all 500 operations have to be performed onto the database at one instance of time, rather than being distributed over the entire lifespan of the transaction. Therefore, there could be potentially heavy disk operations during commits, which could bring down performance, or which could cause the system to thrash or lead to some other such problems. With immediate update techniques, that is where logs are or where the database is updated as and when the transactions are written onto logs, we require both undo and redo operations. So such kinds of recovery techniques are also called undo/redo transaction or undo/redo recovery techniques. Right. Now, what is the general idea behind immediate recovery techniques? The general idea is that as and when the transaction is executing, the database is updated even before commit, which is very important here. That is, the database is updated as and when the transaction is executing, and the transaction may not commit at all. The transaction may become a failed transaction, it may abort, it may have to roll back and so on. However, as and when the transaction is executing, the database is getting updated. What this means is, suppose the transaction cannot commit, suppose the transaction is not able to successfully perform its commit operation, then we need to roll back the transaction. Now, because we are changing the database as and when we are performing the transaction, we have to perform corresponding undo operations. That is, we have to undo whatever changes that the transaction has made to the database. So database updates are performed after the updates are recorded in the log and the logs are written onto disk. And of course, it may not necessarily be force written onto disk, that is you just write it onto log and then write it to the database. Now, once you know that the log has been written to disk, it is safe for you to write to the database. Now, suppose there is a crash at any point in time, and you have to do two different operations. One is you have to undo all unfinished transactions since the last checkpoint, and you have to redo all committed transactions since as you know are different stages in transaction logs, where we say that it is safe to throw away all other historical data that is there in the log, because the log is a monotonically increasing file where every operation keeps on adding to the log. Now, suppose we do not truncate the log, it could well be the case that the log becomes far more bigger than the database itself and becomes far more difficult to manage than the database itself. Therefore, it is important for us to be able to conclusively decide when, at what time, what parts of the logs can be safely deleted or can be safely thrown away. So, that is where the notion of checkpoints also come into the picture. There is a third kind of recovery techniques which we have not seen in detail, but I am including this here for the sake of completeness, which are called undo based of transaction undo variety of transaction recovery protocols. We saw that is undo/no redo. We saw that there was the deferred update techniques was no redo/undo, and the immediate update techniques were undo/redo, and this is undo/no redo. The general idea behind undo based transactions is that it's a recovery technique that is based on pure undo operations. Okay, what this means is all committed transactions are flushed onto disk during checkpoints. That is, sorry, at every checkpoint, in order to be able to safely throw away certain transactions, we flush all committed transactions are maintained, that is the chain of all activities by an active transaction is maintained by what is called as backward chaining in the log. That is, whenever I enter a entry for a particular transaction in the log, I also maintain a pointer to its previous to the previous operation that it performed. Therefore, the way that these log entries are maintained are what are called as compensating log records, are also called as CLRs, where for every update operation you perform, you store what is called as a compensating operation. For example, if you, let us say, debit 5,000 rupees from an account A, the compensating transaction or the compensating operation rather would be to credit 1000 rupees or 5000 rupees to this particular account, right. So for every kind of update operation, let us say you deleted a particular tuple, the compensating transaction would be to insert the same tuple back into the database, the compensating operation. So so you maintain a log of compensating operations, and at every checkpoint you see which are the transactions that have committed and flush them onto disk, so that you don't have to undo them once again. And at any time a system crashes or we encounter a system crash, what we need to do is simply start from the state where the system has crashed and follow the backward chain of logs and perform all the compensating log records, that is compensating operations that are performed. So this is a pure undo based operation where there is no need to redo any transaction or there is no need to redo any particular transaction activity. The redo is performed, or the flushing of transactions data are performed only at checkpoints and not after any system crashes. Now let us look into the notion of checkpoints itself in a little more detail. As we said before, a checkpoint is some point in a log where we say that it is safe to throw away everything before this checkpoint. That is, all committed transactions until this checkpoint are now durable. That means they have been physically committed to the database. Therefore, the records of all committed transactions need no longer be stored as part of this transaction log, and it is safe to throw away all the data about committed transactions. And the frequency at which we take a checkpoint decides or it is some kind of a balancing factor between what is the amount of log that you are going to store versus what is the performance overhead that you are going to incur, because at every checkpoint you need to bring the database to what is called as a quiescent state. That means you have to suspend all activities, all transactions that have committed and ensure that they are physically modified in the database and restart the database system, that is restart all the transaction activities. Therefore, if checkpointing is done at too frequent an interval, if checkpointing is done too frequently, then it impedes performance, while if checkpointing is done at too wide an interval, then it starts increasing the amount of log record that you have to store. So what is the general algorithm for taking a checkpoint? We have to first suspend all transaction activities temporarily, that is we need to take the DBMS to a quiescent state, and then we have to force write or flush all main memory buffers that have been modified of committed transactions actually onto disk, and then write a checkpoint record into the log and force write the log onto disk as well, and then now it is safe to resume transaction activities. But then as we saw that bringing a database system to a quiescent state is a costly operation. Just imagine a large database system, like let us say the database system for railway reservation, let us say for a given railway zone, like say southern railway zone. At any given point in time, there are possibly hundreds or even thousands of transactions that are performing. So many requests coming from different places for reservations and cancellations and or some other kinds of activities, not just reservations and cancellations, let us say rescheduling and so on. So there are several different transactions that are running at any given point in time, and even if we stop the database system, let us say for a few seconds, or even if or sometimes even a few minutes, because the size of the database is so huge, it actually impedes or impairs the activities of a large number of requests. That is, there could be a large number of people waiting in different reservation centers waiting to reserve their tickets, and bringing the DBMS to a quiescent state will actually stall all of them and so on. So there is there are other techniques that are used which can try to obviate the need for bringing the database onto a quiescent state whenever a checkpoint is being taken. Remember, taking a checkpoint is quite important, because otherwise the transaction log itself becomes too difficult to handle, but it does not impede the performance too much, and that is where the notion of fuzzy checkpoints come into the picture. That is, fuzzy checkpoints essentially does not require normal checkpointing requires suspension of all transaction activities, but fuzzy checkpointing does not require bringing the database onto a quiescent state. Essentially what we do in fuzzy checkpointing is that we write the checkpoint entry into the log and we resume operations, but we keep watching the disk itself, that is at the physical layer. For example, note that note that when we write something onto disk, the operating system may not actually physically write it onto disk, it would actually write it onto a buffer cache within the main memory. So it's still volatile, and it will write it onto disk at some later point in time. So we wait until that point where the checkpoint log actually comes onto the disk, and then we start removing all the old entries, that is whatever has to be can be safely removed are then removed then. A second kind of checkpointing which does not require the database to be brought to a quiescent state is also called a non-quiescent checkpointing operation. Here unlike fuzzy checkpointing, there is also no need to watch the physical disk sector or physical disk block for to see whether the checkpoint entry has actually appeared. And but the idea here in non-quiescent checkpointing is that active and non-active transactions at the time of the checkpoint are handled separately. Let us look at how non-quiescent checkpointing actually performs. There are essentially three different steps in this non-quiescent checkpointing. At any time, if I have to take a checkpoint, what I do is I first determine which are all the active transactions at this point in time. That is, these are all the active uncommitted transactions that are currently running, and then make an entry called start checkpoint with T1 to Tk, which are all the active transactions running at this point. Now this entry will go into the buffer cache and so on and so forth, and finally at some point in time will reach the disk. Now wait until and we are not concerned when they are going to reach the disk, and we are not going to watch the disk at all. We just wait until each of these transactions either commit or abort. Okay, but we do not prevent other transactions from starting, that is the other activities could be resuming by themselves, but we simply have to wait until any of this commit or abort. When all of them are done, that is they are finished or terminated, we write a end checkpoint entry into the log, and then force write the log onto disk, that is we flush the log onto disk. Now what is the use of such a checkpointing, that is how can we recover from such a checkpointing? Recovery from such a non-quiescent checkpointing is also quite simple. Let us say at some point in time there is a crash, and we are and we recover from the crash, and we are or we have started the recovery process after the crash, and we start to read the log backwards, that is from the last entry onwards. Now suppose we meet a end checkpoint entry first. What does that mean? That means that the previous checkpointing operation has successfully completed, right? That is, we know that all incomplete transactions that were there at the time of the checkpoint have been completed. Therefore there is no need to do anything, that is it is safe. We just have to restart whatever transactions were running after this time. Okay, but suppose we reach a start checkpoint without an end checkpoint. What does that mean? This means that the crash has occurred during the checkpointing operation itself. Okay, that is at these were the set of transactions that were running, and all of them have not yet terminated, they have not yet committed or aborted, and the crash has happened. So therefore, what is it that we need to do? We have to undo all these operations, that is all the transactions, all the operations that have been performed by these transactions. There again we can use some kind of backward chaining, like we saw in the undo only kind of recovery algorithm, by which we undo all of these operations and until how far behind in the log we need to go. We need to go just until the previous checkpoint, because we know that the previous checkpoint would not have completed until all the active transactions at that point in time have not yet completed. Okay. So therefore we never need to go beyond one checkpoint, that is beyond the previous checkpoint, that is we can safely throw everything else beyond the previous checkpoint, right, and we just have to trace them through the log till the previous checkpoint and undo all these operations. So that is another kind of checkpointing operations that are used in addition to or in complement to the normal quiescent based checkpointing, where you need to suspend all activities of the database system. There is an which is called as shadow paging. It was as part of system in this, but where the technique of recovery is not based on logging, but on maintaining different copies of database pages. That is, the database is managed in terms of different pages or logical entities of disk operation, which pages could be just, let us say, disk blocks or disk sectors or a set of sectors and so on, and we basically make different copies of these pages in order to maintain the log. Okay. So there is no need for write ahead logging, and all updated data are kept in a different location from the original data. They are not kept on the main on the same data set, and recovery basically entails that we discard the new page, whatever is the updated page, and revert back to the shadow original page, that is the shadow of the original page which was still there, that is we do not delete the original page until it is safe to do so, which we will see shortly. Okay. Shadow paging is quite efficient in the sense that there is no need to perform multiple write operations. In log based recovery, you need to first do a write ahead logging and then write onto the database system. So there is a need to perform multiple write operations for every given multiple update operations for every update operation that is involved. But in shadow paging there is no need to do that. However, shadow paging suffers from fragmentation of pages over an extended period of time, and usually we need to defragment the set of database pages by an offline operation after a number of recovery techniques have been executed. So how does the shadow paging technique work? Here is a small illustration. There is we usually keep a page table, that is each page has a particular address where each page can correspond to a set of tuples for a given table, for example. Okay, and each page is given a particular address, and there are two different pointers for each page addresses, what is called as the current page pointer and the shadow page pointer. Initially we just have the current page pointer here and which is pointing to a particular page. Now let us say some tuple in this page has to be modified. So there is a modification request for this page. Now we see that this page has no shadow page. Okay, so therefore what we do is we create a copy of this page, okay, and point the current page pointer to the copy. The original will now become the shadow, that is the shadow of the original page that existed, and we perform the modifications, whatever update operations that we need to do will be done on this page here. Now suppose somewhere down the line when we are using this page there is a system crash. Now when there is a system crash, all that we need to do is to discard this page and go back to the shadow original page, and then change the current page pointer to the shadow pointer here, and set the shadow pointer to null. So we just discard whatever was there and we have gone back to a consistent state. Now you might be wondering at what time are we going to start, how do we know that this is consistent, that is how do we know at what time do we start creating a shadow page. Essentially shadow pages are updated with current pages at every checkpoint, that is whenever there is any checkpointing operation, not just a crash recovery operation, we perform this following operation, that we perform this following set of activities, that is we replace the current page with the shadow page, make the shadow page pointer to null and the current page pointer to the previous shadow page pointer, so at every checkpoint we are flushing the shadow page, or we are updating the shadow page with the new current page, and every first modification after a checkpoint requires creation of a new current page. And as is kind of evident here, the checkpointing operation that is that has to be used here should be a quiescent mode checkpointing operation, that is we need to suspend database activities for performing such a update operation, that is replacing the shadow page with the new consistent current page. There are also other issues during that we have to contend with for crash recovery. What happens, that is the main issue is what happens if there is a crash during the recovery process itself, that is there is a system crash and we are trying to recover the database system and then there is again a crash. Okay. Now in order to be able to handle such issues, that is so that crashes during recovery do not affect the database, we need to be we need to ensure that the undo and redo operations are idempotent. Remember even in the previous session we had used this word idempotent. Idempotent essentially means that no matter how many times you perform the operation, the net effect would be as though you have performed the operation only once. And it does not matter how many times you perform this operation, that is let us say copying an element A to element B is idempotent. No matter how many times you copy it, it is equivalent to saying that we have copied it only once. But there is a problem with idempotent operations as well, that is if we have to make undo and redo operations idempotent, then we have to ensure that multiple transactions or multiple active transactions do not access the same element at the same time, that is one transaction has to wait until a previous transaction has committed before it is safe for it to access a data element, and that actually impedes performance in terms of sync. Okay. And of course in shadow paging technique there is another problem which occurs when there is a crash during recovery, especially when we are manipulating pointers, that is suppose you have discarded the new current page and we are changing the pointers to the old shadow page, and then there is a system crash. It may so happen that all pointers are lost and the page is just has just become garbage, that is there is no way to access the page and basically place it in the context of the larger database. Until now we have essentially talked about system crashes or transaction failures, where the fundamental criteria was that we can lose or we may lose data in the main memory but not in the persistent storage. What happens if there are media failures, that is there is a disk crash, let us say or development of bad sectors. In this case we cannot even rely upon the data to be safe in the persistent storage as well, that is even the data that are there in the persistent storage are gone. Fortunately media failures are much more, disk crashes happen at a far more infrequent fashion than let us say power off or an operating system hanging and so on, and crashes are what are called as archiving or taking backups. and I am sure you would have you know the concept of taking backups. It is simply taking a copy of the entire set of database onto another offline media which is stored physically in a different location. And however, with when you are talking about large database systems, again when we talk about database systems, always imagine a large database system, because most of the problems of database management systems come from their size and not from anything else. So imagine a large database system like a railway reservation or bank or whatever. Now the problem is itself takes a huge amount of time. Suppose I have 1 gigabyte of data in my database, which is quite common. In fact, it could sometimes we even have more than 1 gigabyte of data. We have several gigabytes of data in any operational database, and possibly even terabytes of data. Now copying them to a separate let us say tape media or optical storage takes a huge amount of time, in the order of hours or possibly sometimes even days, to copy the entire set of data elements onto backup storage. And therefore there is a need to perform backup operations in an online fashion. That is, as and when database activities are going on, we cannot obviously suspend all railway reservations, let us say, for 1 day. We cannot say that okay, tomorrow there is, you cannot reserve any train tickets and so on. It has to be on every day, 24 hours a day or 7 days a week or so. Every day or every instance of time the reservation activities are going on. You can book for train tickets over the net, and you can book them over the counter and so on and so forth, right. So there is a need to perform online backup operations. So let us briefly see what is the basic idea behind online operations, and which can help us appreciate the need and the complexities involved in an online backup operation. Before we do that, we need to take up certain definitions. We distinguish between different levels of archivals. Okay. So what we call as level 0 archival and level I archival. A level 0 archival or what is called as a full dump is an entire archival or is a copy of the entire database from onto the archival storage, and a level incremental dump is essentially copying of only the changes that have been that the database has undergone before the rather after the last archival. That is only changes since the last I-1 level I-1 are archived. Now the basic idea behind online archival is shown in this figure. Between main memory and disk there is this checkpointing operations. As you might have noticed the similarity between archival and checkpointing. Checkpointing requires the DBMS system to be brought into a quiescent state, and archival requires a suspension of all database activities in order to copy them onto the archive. Okay. So checkpointing gets data from memory onto disk, and whenever we need to recover, we recover based on logs. And the archival process gets data from disk onto archive, and because it is unrealistic to say that we suspend all DBMS activities during archival, we usually allow the DBMS to keep updating its database operations as and when the archival process is going on. However, in addition to the database, we also store the log from the previous checkpoint until the previous checkpoint in addition to the database onto the archive. Therefore, whenever we need to recover from archive plus log to bring back the database onto the last consistent state before a media crash, and the database is being modified as and when the dump operation is running. So a simple algorithm for online archival is given here. We first begin by writing a begin dump record into the log, that is starting from the logging operation itself. We begin the archival process. We then perform a checkpoint, usually a quiescent checkpoint but not necessarily, and then we flush the log. Okay. That is, we have begun the dump, and begun the checkpoint, that is we have flushed all committed transactions onto the database, and we have a log of all the active transactions here. Then perform the dump, okay, full or incremental, whatever kind of dump from the disk onto the archival data. Now once all data are transferred onto archive including the checkpoint that is there in the log, then enter end dump in the log. So what is the advantage of this? The advantage is shown in this slide, that is during recovery, that is when we have to restore the database. Now the recovery from media crashes is called restore rather than recovery, that is we are restoring the database from the archive. So when we restore the database from the archive, we find the most recent full dump and reconstruct the archive based on all the incremental dumps, okay, and then we write it back onto the database, and then we take the database log, that is the surviving log entry that was also archived in the archives in the archival storage. Now and there we have a checkpoint which shows what all has been done to the database, and whatever was there after the checkpoint we start redoing those database, that is whatever kind of logging method is used, that is suppose we have an undo logs, then we perform the corresponding undo operations, and suppose there was it was a redo log, we perform the corresponding redo operations depending on, let us say it's a deferred update or an immediate update kind of logging operation. So that kinds of summarize. There are a number of other topics in database recovery which we have not touched upon, especially perhaps most significantly the kind of recovery techniques that are used in many of the commercial DBMS systems. Most of the commercial DBMS systems today use a combination of undo and redo logging operations, that is this is to get the right trade off between performance and recovery overheads, because in a pure redo operations you have a performance overhead in the sense that there is a huge spurt of activity during commits for every transaction. Therefore they use a combination of this undo and redo operations, and there is a kind of a famous series of protocols called ARIES, ARIES, which you can possibly search on the internet, which was proposed at IBM Almaden Research Center, which is kind of used quite which is kind of very popular and used in several different commercial database systems. We have not covered the details of the ARIES protocol here for reasons of brevity, but most of the concepts used in ARIES depend upon are based upon several of the concepts that we have studied here, like deferred updates or immediate updates and checkpointing and undo and redo operations and idempotent operations and so on and so forth. So let us briefly summarize what we studied in database recovery under the topic of database recovery. We looked into the idea of transaction states and what are the different states that a particular transaction can exist, and the ACID criteria for transactions, which determine how a recovery protocol should run. And we looked at the different kinds of failures, like say system crashes, media crashes, transaction failures and so on, and for the most frequent kind of failures, like say system crashes or transaction failures, we saw three different kinds of recovery mechanisms, right, that is no undo / redo operations, that is deferred update recovery, and undo / redo, which is immediate update, and there is undo / no redo operations, which are based on compensating log records or CLRs. We also saw the notion of shadow paging, where you do not have the need for a log, therefore it's much more faster, the recovery mechanism or the DBMS itself is much more faster, because there are no multiple write operations or overheads that are involved during every update, but which suffers from possible fragmentation, that is so many pages created at different places in the disk, or possibly when suppose there is a system crash during recovery itself, there is a possibility of encountering garbage system pages as part of the disk itself. So shadow paging has its own advantages and disadvantages with respect to write ahead logging. We also saw the notion of archiving or the idea of taking online backups for handling media failures, where we take a incremental backup and we recover or we restore from backup based on not just the archives but also on the log that brings us to the end of this session.